Hi, Jim Houlis here with Chem 120 on the board. Today we're doing CO2, carbon dioxide. What we're going to do is Lewis dot structure. So what we have to know first to do a Lewis dot structure is the valence electrons. Carbon brings 4 valence electrons to the program, 4 valence. Oxygen brings 6 valence electrons. You can find this out on the periodic table. Since there are 2 oxygens, it now has 12 valence electrons, which gives us a total of 16 valence electrons to use to describe this shape. So in order to draw this molecule in Lewis dot structure, we're going to start with a carbon. Carbon has 4 valence electrons, so I put them here, 1, 2, 3, 4. Now let's add the oxygen. Each oxygen has 6. So I'll make little X's for the oxygen electrons. That makes 6. On this side, I'll add an oxygen, make a single bond, 1, 2, 3, 4, 5, 6. So now I have, let's count them, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've used all my electrons, but they don't follow the octet rule. We can't have that. But what we do have here is we have 2 single electrons on the bottom and 2 single electrons on the top that can come in and form bonds between the carbons and the oxygen. So let's add those now. All right, so now let's count them. 2, 4, 6, 8, 10, 12, 14, 16. So we still have the same number of valence electrons, but now we have a double bond in between them. This is the Lewis dot structure. Notice it's all dots. If you want to write a structural formula, you put lines in, but you still show the lone pairs. Now I switched to dots instead of X's, but they still represent the same thing, the lone pairs on the oxygen. So each oxygen has 2 lone pairs. So we still have the same number of electrons, 2, 4, each bond is 2, 6, 8, 10, 12, 14, 16. However, now we can look at the structure of the molecule, and we can add our electronegativity differences, delta minus and delta plus, right? The slightly positive charge on carbon because most of the electron density is brought to the outside of the oxygen because it's more electronegative. Because this is a symmetrical molecule, it's nonpolar. The molecule, the whole molecule itself, right, the entire molecule, nonpolar. The bonds within the molecule are polar. But don't get those two confused. You can have polar bonds and have a nonpolar molecule if it's symmetrical. All right, so thank you for your attention.